Okay, thank you. Yeah, very good morning to all. Uh, in yesterday, before going to the today's session, so first of all, we'll just review about what is happening in the last class. So in the last class, what we have been seeing is that multi-processor organization may be either independent process organization or it may be a cooperative process organization. A cooperative process is one that can affect or be affected by other processes executing in a system. That implies that both processes are sharing any common resources. That is, both processes are sharing any common resources. It may be a code or it may be a data, whatever it may be. Then after that, then we have been seen about the data sharing problem. Whenever a multiple processes are running simultaneously, if any data is going to be shared by multiple processes at the same time, if you are not using any proper security mechanism for the data will going to be enters into inconsistent state. In order to overcome that inconsistent state, okay, we have been uses a techniques called it as process synchronization techniques. Okay, a process synchronization is a set of tools. Hmm, a set of tools or mechanism to ensure that the data will not enter into inconsistent state. The example what we have been seen in the last class is a bounded buffer problem where a producer and consumer both are sharing a common variable known as a count variable. This variable is value is initially 5. So after producer producing an item, after the count value may be increased and after consuming the item from the buffer counter value will be decreased. Both are sharing this. So after producing one item and consuming an item, again the value has to becomes as 5, but the value is becomes either 4 or 6. This kind of a state is known as inconsistency. In order to overcome this particular inconsistency, okay, so one scientist has been told that a critical section problem, if any algorithm you have been written, that algorithm must satisfy critical section conditions. So what is that particular critical section conditions? In the sense there are three conditions: mutual exclusion, progress requirement, bounded waiting. So mutual exclusion in the sense if any process is executing in its critical section, okay, no other process is allowed to enter into their critical sections. That is, the maximum number of processes that can be allowed to enter into their critical sections is only one process at a time. And after that, progress requirement. Okay, whenever the CPU becomes idle, you need to select one job from ready queue and supply the CPU and make the CPU busy at all the times. So first of all, you need to give a first priority for the processes. Those who are trying to enter into critical section. Those who are trying to enter into critical section. And number three, bounded waiting. There exists a practical limit on each and every process that can be allowed into the critical section. That's why again the process is redefined as okay, like this, a process is simply redefined as it is a continuous collection of critical section followed by remainder section, critical section followed by remainder section. So in critical section preceded with an entry section and followed by an exit section. So entry section in the sense it simply indicates that whatever the set of resources which is required, okay, whatever the set of resources which is required, that resources is going to be allocated to that particular process, going to be called it as entry section. Once the resources has been successfully allocated, then it will going to be executed in critical section, and after the releasing of resources is in exit section. This is what we have been seeing, and after that we have been applied this as a written a solution for two processes. So first solution is only satisfies mutual exclusion, second solution satisfies progress requirement, and all the three possibilities are going to be satisfied in the third algorithm. This is what we have been seeing, and followed by we have been seeing synchronization hardware. Okay, so the best one, all solutions are synchronized hardware based on locking mechanism. Simply, what is this one? Before executing any particular process, first of all, whatever the data items you are going to be required, make a lock on these data items. So then you are allowed to continue your execution. Once your execution is successfully completed, you can release the locks. That's why again the process is redefined as okay, acquire the locks on the data items, then enter into critical section and release the lock, and after that you can enter into remainder section. This is the code what we have been seeing, that simply true or false. If in case true, it is already held by someone, and if it is false, that particular process is not done, that particular data is not locked by any one of the process. Okay, this is what you have been seeing. Now, coming to the today's session is that, okay, synchronization tool. Another very important synchronization tool is that semaphore. So, what is a semaphore? A semaphore. Okay, okay. This is a very important and more sophisticated for synchronized activities. What is a semaphore? A semaphore is a synchronization tool. First of all, a semaphore is a synchronization tool. It is a small variable. You may call it as S. It is a small variable. Yes, is an integer variable. Apart from initialization, it is accessed by using only two instructions, wait and signal. Generally, wait is represented with P and signal is represented with V. So we will see the detailed discussion about what is this wait function and what is this signal function. Before going to this particular one, a very simple logic is that this S variable is initialized with 1. This S variable is initialized. Semaphore is a small synchronization variable which is having either 1 or 0. 1 in the sense, okay, that present this particular variable is not locked by any one of the process. And in case if it is equal to 0, if synchronous semaphore variable is going to be 0, it is already locked by someone. It is already locked by someone. This is a simple logic. A semaphore is a small variable that is attached to each and every common resource which is shared by more than one process at the same time. That variable value is either 1 or 0. If semaphore value is equal to 1, that indicates this particular variable is not accessed by any one of the transaction. This particular semaphore value is equal to 1, that indicates this value is not locked by any one of the transaction. In case if it is 0, that implies it is already locked by someone. That is a very simple thing. Okay, or you can call it as if semaphore value is equal to 1, the maximum number of people that can be allowed is only one person at a time. That is, in case if the semaphore value is equal to 0, that implies it is already locked. No one is allowed to access this particular variable. Now, this apart from initialization, the semaphore value can be accessed or modified by using only two functions, either wait or signal. Okay, either wait or signal. So let us take an example. Okay, if the semaphore value, suppose X is a variable which is shared by two processes P1 and P2, and a small semaphore value is attached to that particular X variable. Initially, that X variable is not accessed by anyone. That's why the semaphore variable which is attached to the X is initially 1. Semaphore value is 1. That implies this particular variable is not accessed by anyone. Suppose if process P1 make a requisition to the operating system, I want X, then immediately operating system checks that what is the value of semaphore of X. The semaphore X value is now 1. That implies at present it is not accessed by anyone, and then immediately it allocates the X variable to process P1, and after immediately allocating, the semaphore value becomes 0. And after the process P2 make a requisition, I want to access the semaphore variable. Okay, I want to access X. Then immediately operating system checks that what is the semaphore value of X. Then immediately it finds that the semaphore value is now 0. That implies it is already locked by process P1. Now we are not allowed to continue the execution. Then operating system simply put the process P2 in waiting state. The operating system will simply put the process in waiting state. Okay. Now, so once a process once process P1 has been completed a task, then it will immediately tell you that my task is done. Okay, my task is done. Immediately operating system will change the semaphore value from again 0 to 1 and gives a signal to process P to come. You can use this particular variable now. That's enough. This is okay how it is going to be happen. That implies this particular X variable is now accessed by only one process at a time. It is 100% guarantees that the data does not enter into any inconsistent state. That's it. So now, sir, how can I access this particular semaphore variable? In case if any process required any particular common resource, it first of all issues a wait function, the wait system called to operating system. So I am waiting for this semaphore variable. So then immediately the operating system checks that what is the semaphore value. In case if it is equal to 1, immediately sanction that particular resource. If it is not equal to 1, you have to wait until the value becomes 1. That's it. Once your process execution has been completed, again the process will going to return that particular semaphore value by using a function called a system call function signal. Now, how this particular wait function call has been, this is a small piece of code. Anyone can write this particular one. Wait is a function which takes one semaphore value as an input. Suppose if process P1 is requesting for any particular variable X, then immediately it checks that what is the semaphore value. If S value is initially not it is less than or equal to 0, that implies S value is less than or equal to 0. That implies now it is already locked by someone. You are not allowed to enter into the critical section. That resource is not sanctioned to you. You have to wait until this particular semaphore value becomes 1. Okay, so in case if it is already locked, what is the semaphore value? It is 0. 0 less than or equal to 0. That implies we are not allowed to go on operation. Why? Because it is already used by someone. Suppose if it is equal to 1, okay, it is not locked by anyone. That is, 1 is less than or equal to 0. No, the condition is failed. Immediately, you are entered into critical section by making S is equal to S minus 1. Now 1 minus 1, semaphore value becomes 0. If any person is trying to again enter it, then the semaphore value is 0, so that that particular guy is going to be simply structured in this value. So the simple logic is that S is equal to S minus 1. Suppose if the process has been successfully completed operation, if the process is successfully completed its operation, then it issues a system called as signal. So what is that signal? So now the semaphore value is 0. 0 plus 1, 1. 1 indicates that now the resource is idle. Now anyone can use this one. This is a simple logic how they have been implemented. Okay. So what is a semaphore? A semaphore is a synchronization tool. It is a small integer variable. Okay, apart from initialization, this particular variable is accessible by using only wait and signal. So before executing any particular process, whatever the common variables you require, you have to make a requisition for semaphore variable of that common resource using await system call. Once your execution has been successfully completed, you have to return back the semaphore variable of that common resource or a data using a system call for it as signal. Is called it as signal. That's it. Now, this kind of semaphore is also going to be called as we are also having this particular semaphore is going to be having only two values, 1 or 0. That is 1 in the sense it is free, and 0 in the sense it is already locked. This kind of a semaphore, and where the semaphore value is going to be lies between 0 and 1, where the semaphore value is lies between 0 and 1. Such kind of a semaphore are going to be called as binary semaphore. Such kind of semaphores is going to be called as binary semaphores. Okay, now in case if the semaphore value is not restricted, it can be any value, then such kind of a semaphore is going to be called as counting semaphore, where the integer value of a semaphore can range over unrestricted domain. Then it is going to be the range over unrestricted domain. That is going to be called as counting semaphore. So actually, so far what the solution we have been seeing, it is only binary semaphore. Now we are going to see how to solve synchronization problem. Okay. Can solve various these semaphores can solve various synchronization problems, but it is also having a small problems. Let us take a small example. Okay, in order to better understanding of this one, let us take P1 and P2 that requires S1 happen to be before S2. Okay, both are sharing a common resource. Both are process P1, process P2, both are going to be sharing a common resource. Okay, now already we have been designed a program in such a way that the statement 1 is executed before the statement 2. So both are statement 1 and statement 2 are sharing a common resource. So create a semaphore is initialized with something 0, whatever it may be. Okay, now semaphore statement 1 is executed. So after that, immediately it is releasing the semaphore value. And meanwhile, the process P2 is first of all initially waiting for synchronization variable. Once it is obtained, then it is allowed to continue. This is the piece of code. How do you write this one? That's why again the process is going to be redefined as like this. Okay, now repeat until false. Now, so this particular semaphore variable sync, a synchronization variable, It is a mutually exclusive variable. This variable is accessed by only one person at a time. Okay, this variable is accessed by only one process at a time. This variable is accessed by only one process at a time. That's why I can call this one as a mutually exclusive variable. That's why now the process is written as, now I am waiting for the mutually exclusive variable, which is once this particular semaphore has been successfully allocated for me, then I am going to enter into the critical section. Once immediately after my critical section, again I need to release this particular semaphore variable. This is called as the release is going to be done by using signal. That is done by using signal. The entry section, okay, waiting for mutex variable is going to be called as an entry section, and releasing the particular mutex variable is going to be called as exit section. Is going to be called as exit section. And remainder section can be executed anytime. There is no problem. Why? Because while executing this kind of an instruction, the CPU, okay, remaining no other process is going to be suffered at all. Okay, so or you may, this is waiting for a mutex, enter into the critical section, and after that signal the mutex followed by reminder section. This is what is a process is redefinition. Now we are going to be semaphore practical implementation. In case if any data is going to be shared by more than two processes at the same time, how can you protect it? Okay, so you must guarantee that no two processes can execute wait and signal on the same semaphore at the same time. Okay, now in this particular semaphore implementation, what we're going to see is that, okay, whenever a data item is going to be accessed by multiple processes at the same time, how can you see this one? Okay, how can you protect that particular variable? This can be done by using counting semaphore. You know what is counting semaphore? Where the semaphore value is an unrestricted domain. Semaphore value is unrestricted. Whereas in the case of binary semaphore, the semaphore value is always lies between 0 and 1. The semaphore value is always lies between 0, 1, 1. The main disadvantage of the above solution, what we have been seeing is that they are going to be suffers with busy waiting. While a process in its critical section, other process that tries to enter into the critical section must loop continuously in the entry code itself. The entry code itself. The continued loop is clearly a problem in the real-time multi-programming system. Okay, this kind of a thing is also going to be called as spin lock. Okay, why? Because the process spins while the process spins in while loop, waiting for the lock. The advantage of spin lock is that no context switch is required when a process must wait on a lock. That is a very important beautiful point. Is that so? While you are waiting, there is no context switch. You are simply stuck in while loop. You are simply stuck in while loop. There is no context switch. Why? Because okay. So there is no context switch is going to be required. So you know what is context switch? Saving and restoring. There is no saving and restoring is going to be done. The CPU cycles is simply unnecessarily wasting. The CPU cycles are unnecessarily wasting for this particular cycles. Now, to in order to work on this particular problem, busy waiting, we can modify the definition of a wait signal of semaphore. Okay, when a process executes a wait operation and finds that semaphore value, okay, depending on priority must wait. Now we'll see how do you define it. Before going to the detailed discussion of a multiple process solution, that is counting semaphore, first of all, you must guarantee that no two processes, these are the precautions you need to be take before trying to implement a solution for a counting semaphore. So you must guarantee that no two processes can execute wait and signals on the same semaphore at the same time. That is the first very important one. Next. And coming to the next very important one is that the implementation becomes a critical section problem where wait and signal code are placed in critical section. So you are telling that wait and signal cannot be done in simultaneous manner. That implies this wait and signal must be executed in a critical section. You know what is critical section? In case if any process is executing in its critical section, then no other process is allowed to execute in their critical section. That implies the maximum number of processes that can be allowed to enter into the critical section is only one. So what I say is that wait and signal functions cannot be executed at the same time. That implies wait and signals functions must be kept it on critical section. That implies while executing wait function, no one is allowed to use signal, and while executing signal function, no one is allowed to issue wait function. That is, so this is a very one. So what is okay? The implementation becomes the critical section problem where wait and signal code must be placed in critical section. That implies so okay, while executing wait, no one is allowed to execute signal. While executing signal, no one is allowed to wait. With each semaphore, okay, and the third very important point is that okay, with each semaphore, there is an associated waiting queue. What is this waiting queue? The list of processes waiting for this particular semaphore value. Okay, earlier we have been seen a binary semaphore. Okay, binary in the sense only two processes we have been seen. Yes or no? Now the list of processes who are waiting for this particular semaphore value has to be kept in a queue. And once the resources becomes free, we need to allocate this particular semaphore variable to any one of the waiting process. Any one of the waiting process that may be done depending on priority, whatever it may be. That is, so you need to maintain another thing is called it as waiting queue. What is this waiting queue? The list of processes which are waiting for this particular has two data items. Each entry in a queue has two data items. What is the value? What is the pointer to the next record in the list? Okay, what after executing this particular process? Okay, so what is the next process going to be executed? Okay, what is the next process is going to be executed? What is the next process is going to be executed? Now, let us take. Now, coming to the next one, two operations. So we are also having another two operation. We have been already seen two system calls. That is, one is wait and second one is signal. And we are also going to see another two system calls, going to call it as block and wake up. So what is this particular block and wake up signals? Okay, block is a system call. Place the process invoking the operation on the appropriate waiting queue. Okay, and wake up. Remove one process in the waiting queue and place in ready queue. In the ready queue. Now what is this? Suppose if a process requesting for a resource. If a process is requesting for a resource. If a process requesting at the time the process is going to be already the resource is already allocated to some another process. The resource is already allocated to some other process. Okay, then the operating system will simply ask you to wait. But after some moment of time, again this process make a requisition to the operating system. I require this resource. Again, operating system will going to be simply checks that and we ask him to wait. But CPU cycles is unnecessarily wasting for checking the semaphore value. That's why what the operating system will going to be do is that simply issues a block system call, and this process requisition is blocked until the semaphore value becomes free. You are not continuously allowed to give an interrupt to the or give a system call to the operating system for the semaphore variable. Once the resources becomes free, the operating itself will give you a system call it as wake up. Operating system will going to be simply gives you a wake up system call. Then immediately you are going to be removing one process from the queue, the waiting queue, and put the job in ready queue for execution. This is what is happening. So totally we are using four system calls. This is wait, and this is signal. Okay, this is signal, and another one is block, another one is wake up. Now we're going to be see how to implement the piece of code. Now I haven't simply I'm defining a structure. Okay, a value and the list of processes. This is waiting for this particular semaphore variable. I have been defined it as a semaphore. Now the wait is implemented like this. Simple. Okay, initially semaphore value is going to be initially 1. That implies at the time the semaphore value is not locked by any one of the process. So in case there are n processes are running, P1, P2, so on up to Pn. If first of all P1 make a requisition for semaphore variable, at the time the semaphore value is 1. So immediately the semaphore value is sanctioned to the immediately semaphore value is sanctioned to P1. That semaphore value simply becomes as 0. Okay, now P1 is allowed to continue the execution. Now the semaphore values becomes 0. Now, okay, P1 is executing in its critical section. Now process P2 makes a requisition to a semaphore variable. Now at the time the semaphore value is equal to 0, 0 minus 1, that is equal to minus 1. So now minus 1 in the sense there is one person is waiting for this semaphore variable. Another person is making a requisition for this particular semaphore variable. Then immediately minus 1 minus 1 that becomes minus 2. That implies minus 2 indicates okay there are two persons are waiting in the semaphore. Okay, so on up to like this. Okay, this is whenever a process requesting for a wait system call, the semaphore value is decremented. In case if it is not equal to 0, then it is the process is simply put in a queue and ask him to wait. In case if any process has been successfully completed, then it releases the resource. Then semaphore value is automatically incremented by 1. So semaphore value is automatically incremented by 1, and any one of the process is removed from the queue and again supply the CPU. Now we'll see how the semaphore code is. Suppose initially semaphore value is equal to 1. So no one is using this particular semaphore variable. First process P1. First process P1 make a requisition for the semaphore variable S. Immediately S value is equal to minus minus. That implies 1 minus minus, it becomes 0. 0 less than 0? No. 0 less than 0? No. That process is going to be enter into the critical section. Suppose after entering into the critical section, process P2 make a requisition for semaphore variable S by using a system called wait S. Now the semaphore value is 0 minus minus, now it becomes minus 1. Minus 1 is less than 0. Then add this process in your linked list and ask him the queue waiting state and block by itself. Block in the sense, please don't try to continuously make a requisition to the operating system. Once the resources becomes free, once the semaphore value becomes free, then the operating system itself it will going to be wake up you. Don't continuously knock the CPU for this particular semaphore variable. Suppose another process comes and ask for the semaphore variable S. Now the semaphore variable is minus 1. Minus 1 minus minus, that is equal to minus 2. Minus 2 is less than 0. Again this process is for this condition is satisfied. Again this particular process is put it under queue. This process is put in queue and block then themselves. Suppose in case if the first process has been completed, immediately it issues a signal called as signal. Then one signal. Now the semaphore value is minus 2. So minus 2 plus plus, then minus 1. Minus 1 is less than or equal to 0. That implies some people are waiting in the queue. Remove any one of the process from the serial list and give a wake up signal to continue the execution in critical section. That's this is how it is going to be implemented. Now this particular semaphore technique is very simple, but it is also facing with a small problem called it as deadlock. Okay, you know what is a deadlock? A deadlock is simply defined as a continuous waiting state of a particular process is known as deadlock. A continuous waiting state of a particular process, known as process, or you can define it as, you already know that what is a process. A process can be thought of as it is a program in execution. In order to execute such kind of a process, it requires resources like CPU cycles, memory cycles, and IO devices, etc. So whatever the set of resources you are going to be required, first of all, you have to make a requisition to the operating system. I want these resources. At the time the resources are available, there is no problem. If in case resources are not available, then operating system will going to be put your processing wait state. There may be a chance that this wait state is not going to be changed forever, hence it is going to be called as deadlock. Okay, deadlock can also be defined in a different way in a multi-programming environment. Two or more processes are concurrently running. In case if any process is holding some resource and waiting for the resource handled by another process, similarly that process is also holding some resources and waiting for the resources handled by this process, then both processes are not allowed to continue the execution. Hence, this is indefinite blocking. It is going to be called as a deadlock. That is, two or more processes are waiting indefinitely for an event that can be caused by only one of the waiting processes. It is going to be called as deadlock. Let us take an example. There is two variables are there, S and Q, two semaphore variables initialized with 1, two semaphore variables, and there are two processes are running, P0 and P1. There are two processes are running in my computer system. That is, one is P0 and second one is P1. Both P0 and P1 requires S and Q semaphore variables. Okay, both P0 and P1 requires S and Q variables. Both P0 and P1 as in. What happens is that suppose if P0 is hold a lock on S and waiting for Q, And similarly, process P1 is holding a lock on Q and waiting for S. And P0 is waiting for signal Q and P1 is waiting for signal S. Then both processes are not allowed to continue their execution, and this particular situation is going to be called it as deadlock, or may call it as deadlock. Okay, deadlock starvation also. Okay, what is this? P0 is holding S and waiting for Q, and that implies P0 is waiting for signal S. Similarly, process P1 holding Q and waiting for the semaphore variable S. That implies P1 is waiting for the signal. Yes. So this guy is waiting for signal S, this guy is waiting for signal Q. This guy is not releases okay, yes, and this guy does not release Q until their execution is complete. And these two processes enters into a deadlock situation. This is called as indefinite blocking. A process may never be removed from a semaphore queue in which it is suspended. Such kind of a situation is going to be called as starvation. Now, how can you overcome this pattern? Now, we have that implies the locks are always going to be obtained by high priority processes. The locks are going to be semaphore variables is always locked by high priority. Then what happens about low priority processes? Low priority processes are always waiting for high priority has to be completed. That, but never, in case if the low priority process never gains a control, then what happens? Then we'll go up for aging concept to improve the priority. That's it. Now, what happens? Let us take an example. In this, while executing a low priority process, a high priority interrupt has been encountered. What you need to do? Immediately, the low priority process is preempted and the response is given to high priority process. But in this situation, what happens is that if a low priority process is holding a lock on some common data, if you are forcibly stopping the execution of this low priority and giving the control of the CPU to some another one, then what happens is that the data is again in inconsistent state. In this situation, the high priority process must be wait until the low priority process has been completes its critical section. In case if you take a forcibly, what happens is the data is inconsistent. That is the reason. Now, in this situation, high priority process must be wait until the low priority one has to be completed. High priority process must be wait until the low priority one has to be completed. This kind of a technique is going to be called as priority inversion. This concept is going to be called as priority inversion. This kind of a concept is going to be called priority inversion. Normally, the low priority process has to be wait until high priority one has to be completed. But whereas in the case of a semaphore variable, in case of semaphore variable is locked by, semaphore variable is already accessed by a low priority process. In this situation, a high priority process must be wait until the low priority one has to be complete. So this is also known as this kind of a solution is implemented in priority inheritance protocol. This kind of a thing is going to be implemented in priority inheritance protocol. Okay, that is a separate discussion. It is not required here. Now we'll move on to how these particular semaphore solutions can be used to solve classical problems of synchronization. Now, this semaphore variables, this semaphore solution, how it can be used to solve classical synchronization problems. What are the various problems we are going to be see in classical synchronization problems? There we are going to be. It is a large class of concurrency control problems. It is a large class of concurrency control problems. Among that, we deal only 3 problems. Generally, an operating system must implement all this. Number 1, bounded buffer problem. Already we have been discussed in the earlier. Okay, in bounded buffer problem, the buffer is going to be shared by producer and consumer. So, producer and consumer buffer going to be shared by using a common variable count. So, producer is always incrementing count and consumer is decrementing count. If you are not using any proper security mechanism for the count variable, which can be used to tell that when the buffer is full and when the buffer is empty. Okay, so in case we are not using any proper security mechanism for the count, the data will going to be enters into inconsistency. And how can you overcome that problem? By using semaphores. We'll see now. Similarly, reader writer problem. A variable can be read by any number of people at the same time. There is no problem at all. Concurrent readers are allowable. but concurrent operators are not allowable. Suppose let us take an example. Whenever a data item is shared by multiple processors at the same time, if multiple readers can be allowed to access the data variable at the same time. So if one reader is already reading, any number of readers is eligible. There is no problem. But no writer is accepted at the moment. That is first one. And case number 2, if one writer is performing a write operation on the data, a common data item, then no reader or writer is allowed to make an operation on the time. That implies read is no problem. Read write, write read, write write. Any one of the operation is right, the data is inconsistent. So see, concurrent readings are allowed, concurrent operators are not allowed. Okay. If one reader is reading for a data item, any number of readers is allowed to read the data item, but no writer is allowed. If one writer is writing, no reader or writer is allowed to make a operation on the data item. That's enough. In case if you are not following this particular rule, the data is in inconsistent state. How can you protect this? We'll see now using semaphores. Now, dining philosophers, it is another classical synchronization problem. Okay, we'll see with an example of dining philosophers. Okay, now coming to the next one, a bounded buffer problem. There is n buffers, each can having a capability of holding one data item, which is to be take a printout. Now I have been used one mutex variable initialized as one, semaphore variable initialized to value 1. This variable is accessed by only one person at a time. Okay, and I'm using another semaphore variable. Okay, full, initialize the value to 0, initialize the value to 0. That indicates that the initialize the value. It indicates that whether the buffer is empty or not. Okay, whether producer is allowed to place any item on the buffer or not. Okay, that is another one. A semaphore empty is initialize it to the value of n. That implies your buffer is having a capability of holding n items. If the buffer is equal to n, consumer is allowed to retrieve any particular item from it. Now, we'll see how to implement this particular one. I have been totally taken 3 semaphore variable, mutex, full and empty. Mutex is used to protect the count variable. Where producer is making count is equal to count plus 1. Consumer is making count is equal to count minus 1. To protect that, we use mutex variable. Full is a variable. Full in the sense it is not indicating that the buffer is full. Okay, producer is, in case producer is allowed to place one item on the buffer. There is a space for placing an item into the buffer. That indicates. If empty, in the sense it is not empty. Okay, now consumer is allowed to retrieve an item from the buffer. Now we'll see with an example. Now, suppose if producer want to produce an item into the buffer. So first of all, you need to check that whether buffer is having a space for placing an item onto the buffer. Buffer is having a space for placing an item. Producer produce an item. Then first of all, I am checking that weight empty. First of all, okay, weight empty in the sense I am not indicating that for placing an item into the buffer. Okay, understood everyone? Weight empty in the sense I am not saying that buffer is empty. At least there is one place is there for placing an item. There is once. In case if buffer is having a sufficient place for placing an item, immediately you are not allowed to enter into critical section. Then you need to change the variable of count. So if you want to change the variable of count, then at the same time if the consumer is want to change the item value, then what happens? That count value data is inconsistent. That's why I'm waiting for mutex variable. Once the count mutex variable is obtained to you, then you are allowed to continue the execution. Once our execution is successfully completed, you need to release the semaphore variable of count, that is mutex, release. And after that you indicate signal full. Full in the sense buffer is not full. Yes, there is one item for consumer retrieve from the buffer, okay, and take a print. That is full indicates that yes, now consumer is allowed to take an item from the buffer. This process is repeated until it becomes true. Total values are complete. So consumer is waiting for this full. Now see, producer is issuing a signal full. That is, consumer is waiting for that. Yes, wait full. So once you have an wait full, that implies waiting for full in the sense, yes, at least one item is there for consuming from the buffer. Wait full indicates that at least one item is there for consuming from the And immediately once item is there in the buffer, you are not allowed to enter into the critical section. You need to get the semaphore value of count to decrement the value of count. So now we are issuing a command called it as wait mutex. That is, we are getting the semaphore value. Now count after placing the removing the item from the buffer, count is becomes count -1. Then you need to release that particular count semaphore variable. And after that again empty, signal empty. What is signal empty? There is a space for placing an item into the buffer. Now for this system call, he is waiting. Now you see, he is given signal empty, he is waiting for empty. He is given signal full, he is waiting for full. That's it. Like this. Both are going to be communicate with each and every other. Okay. This is going to be called it as process communication. You can call it as. Now there is no process of inconsistency. I can solve this bounded buffer problem simply by using three semaphore variables. Number one is mutex for count, and number in order to place an item, I use a full variable. In order to retrieve an item, I use an empty variable. These are the three semaphores which can be used for protecting, okay, your solving bounded buffer problem. Next, the second very important classical synchronization problem is that reader-writer's problem. So what is reader-writer's problem? So before going to the reader-writer's problem, so first of all you must know that, okay, whenever two operations are said to be inconsistent, any one of the operation is right. Any one of the operation is right. That is the first very important thing you must know, that read is no problem. Read, write, read, write. In these three situations, the data is in inconsistent state. We'll also deal this particular problem in DBMS by using locking techniques. We'll see that topic in your DBMS. Now, how can you explain this particular reader-write problem? Now, a data set is shared among a number of concurrent processes. I'm assuming that one data set has been shared by a number of processes at the same time. Concurrent in the sense all processes are allowed at the same time for execution. All the processes are allowed for simultaneous execution. Okay, now readers only read the data set. Reader in the sense he can eligible for making only read operation. He do not perform any update operations at all. This guy is a reader. In case if any process is said to be a reader, that implies that process is only eligible for reading the contents, is not allowed to update anyone. Writer in the sense, in case if any process is said to be writer, he can eligible for both read and as well as write. Okay. Now the problem is allow multiple readers to read at the same time, but only single writer can access the standard data at the same time. If a person, okay, the data item is read by any number of people at the same time. That is why, because no one is making an updation on the data item. That's why the data is always in consistent state. There is no problem at all. If any single person is making a write, at the same time, if no other person is eligible for making a read or write, in case if you do like that, the data is going to be in inconsistent state. The data is in inconsistent state. So now, in order to overcome this particular problem, in order to overcome this data sharing problem, now we'll take one semaphore. Read-write mutex is initialized with 1. Okay, read-write mutex, that is mutually exclusive variable. Semaphore mutex is initialized by 1. We'll take another integer variable read count, initialize it to 0. We'll see 1, 1, 1. Now, what is this read count? Initially, read count is equal to 0. If one person making a read, then initially immediately read count becomes 1. If another person is making a want to read, then immediately the read permission is sanctioned. Now read count becomes 2. If another person want to read it, again the read permission is sanctioned. Now count value becomes 0. Sorry, count value becomes 3. So the number of readers now is 3. Suppose if any person want to make a write, sorry, no one is allowed. If count value, read count value is equal to 0, there is no reader is reading. If now the read count is 3, that implies the 3 readers are reading. At that moment, no writer is allowed, no writer is permitted to access this one. The writer is put in wait state. That's it. If one reader is completed its read operation, now the count value becomes 3 minus 1, 2. Another reader is completed, again 2 minus 1, 1. Another reader is completed, 1 minus 1. Now the read count value becomes 0. Once the read count is becomes 0, then if anyone is making a requisition for write, then immediately a write lock is obtained on that, then write operation is allowed to continue. Now while performing a write operation, if any person making a read or write, CP does not allow you to continue your operation. Okay, that's enough. This is, now you see that every reader before reading is implementing count is equal count plus 1, read count is equal read count plus 1. After performing a read operation, he issues a command read count is equal read count minus 1. Now all readers are sharing a common variable read count. So before reading, they are incrementing the count value. After performing reading, they are decrementing the count value. Agreed, everyone? Now, so if you are not using any proper security mechanism for this read count, the data is in inconsistent state. Same problem in bounded buffer. Okay, already read count is 5. Suppose another person is read it. Now count value becomes 6. Another one is completed a read operation. Again, it has to come back to 5. If you are not using any proper security mechanism for this read count, the value is either 4 or 6. You know that earlier example, same manner. In order to protect this particular variable, again we are using another semaphore, that is mutex, mutually exclusive variable. We are using mutually exclusive variable. This is for read write mutex. Once a person is making a write, no one is allowed to read or write at the same time. Is it clear? This mutex is for protecting count, and this mutex is for protecting read write operations are not simultaneously allowed. Okay, now before going to the solution of this particular reader writer's problem, online class in order to before going to the detailed discussion about this solution, so first of all, okay, you need to keep this particular 2 points in your mind. The first variation, no reader kept writing unless writer has permission to use a shared object. Okay, any number of readers is allowed at the same time. The second variation, once a writer is ready for making write, as soon as it has to be completed its write operation. Why? Because all readers and writers are blocked for your writing process. This is a very important 2 points you need to be kept on your mind before going to the solutions of this particular reader writer problem. Is it clear? No reader kept waiting unless writer has a permission to use the shared object. Okay, so any number of readers is eligible if no one is obtained a permission on write. Okay, and the second variation is that once a writer is ready, it performs a write as soon as possible. Now we'll see the solution. The writer process is very simple. Waiting for read write mutex. That implies at that time no reader or writer is performing an operation on the data item. Is it clear, everyone? I am taking a semaphore variable read write mutex. That implies at the time no reader or writing making any operation on the data item. In case no reader or writer is there, then you are allowed to continue in the critical section. Once your critical section is completed, now you need to release your semaphore variable read write mutex. Is it clear? So writer process is very simple. Now coming to the read write reader process. If any process want to enter into critical section, first of all, he has to wait for the mutex variable of read count. You have to get the semaphore variable of read count. The semaphore variable of read count, we name it as mutex. The semaphore variable of read count variable is mutex. Once this mutex is obtained, then read count is equal to read count plus plus. If read count is equal to 1, that implies you are the only one person now presently reading. No one is there. That implies then you can eligible for promoting write. Why? Because there is no other readers are there, no writers are there. Then you can make a requisition. I am waiting for read write mutex. At the time it is available, it sanction you. Otherwise, it is not allowed you. Now, so once this read count is incremented, then you need to release this particular read count variable. I haven't released it. After that, I am eligible for performing read operation. So after performing read operation, again I need to decrement the value of count. So before decrementing the particular value, First of all, I need to obtain the semaphore variable of count. The semaphore variable of count is mutex. The semaphore variable of mutex is count. Count. Now read count. So you need to get that the semaphore variable, and after that the count value is decremented. Count value is decremented. If read count is equal to 0, then you can issue no reader is reading now. If anyone is waiting for write, you can give for read write mutex. This guy is waiting for this one, and this is happening. Now, and after once the read count is decremented, you need to give signal mutex. That's it. This is what is the code is. So now, while reading, one person reading, and any number of readers is allowed. While no one is eligible for writing. One person is making a write. No one is allowed for reading and as well as writing. This is how we have been solved reader writers problem. Now we move on to the last problem, and this is dining philosopher's problem. What is this particular dining philosopher's problem? There are 5 scientists are there. This particular people are having only 2 tasks in their real time: thinking. Whenever they feel hungry, they are eating. The philosophers spend their lives for alternating thinking and eating. They are completely sacrificing their lives for the people. They are completely thinking and eating. They are always trying to invent something new. Don't interact with their neighbors. Occasionally, okay, these particular people don't try to interact with the people occasionally, and try to pick up 2 chopsticks one at a time, okay, to eat from a bowl. Suppose let us take each and everyone has been having some rice on their plates, and each one chopstick has been placed in between these particular plates. In order to eat this particular thing, everyone needs 2 chopsticks for eating, but only there are 5 chopsticks are there. If everyone is holding 1 chopstick, what happens is that every philosopher is holding 1 chopstick and waiting for the chopsticks followed by some other one. Then no one is allowed to eat. Then all processes are going to enter into deadlock. Now there is shared data. That is a bowl of rice. So in case they want to pick up the rice and put it on the bowl, what needed to do that? They needed 2 chopsticks. So if everyone is holding 1 chopstick and waiting for another chopstick, the data is going to be in deadlock state. So a bowl of rice is a data set. So in case you want to put the rice on their plates, what they need to do? Okay, they has to pick up 2 chopsticks. So now I have been defined a semaphore variable. Chopstick 5 is initialized as 1. That is, all 5 semaphore variables has been declared. Now how have been implemented? If process PI want to enter into the critical section, that implies they want to eat, and this thinking is going to be called as a remainder section. There is no problem if one person is thinking, and similarly at the same time remaining persons also can think it. There is no problem. This is, let us take an example. If a process PI want to enter into the critical section, he wants chopstick I, and he wants to immediately write the chopstick. You want immediately write chopstick. That implies process P0 is holding chopstick 0 and waiting for, suppose, and in case process P0 want to eat, it requires chopstick 0 and 1. If process P1 want to eat, 1 and 2 is required. So on up to like this. Okay, if process P4 want to eat, it requires 4 and as well as 0. That's why if the process PI want to enter into the critical section, first of all, he has to hold a lock on. Okay, first of all, he has to waiting for chopstick I, and next chopstick I plus 1 mod 5. It is in circular manner. That's why we use modular 5. If both chopsticks are sanctioned from the operating system, then you're allowed to eat. Once your eating is complete, that is your critical section is completed. Once your critical section is completed, again, you need to release the 2 chopsticks. You need to release the 2 chopsticks, and after that you can enter into remainder section. That's enough. This is simple solution. Of course, okay, it may causes deadlock, and starvation is also possible. At worst, it may cause starvation is also. That's it. This is completes our discussion about process synchronization. This is completes our discussion about process synchronization. Now we move on to the next topic of discussion is that deadlocks. Next we'll move on to the next topic of discussion is deadlocks. Okay, so in this session, what we have been seeing is that process synchronization. So, a hardware tool we have been choose that is test and set log, and we have been seen semaphore tool, and by using semaphores we have been solved three problems. Number one is bounded buffer problem. Number two, read and write it problem. Number three, planning philosopher's problem. That is completes our discussion. Now coming to the last topic of discussion and process management is deadlocks. So now we'll move on to the last topic of discussion and process management is the deadlocks. We have been completed process scheduling, process synchronization. Now the last topic is deadlocks. Now before going to the detailed discussion about deadlock things, now we'll define the various standard definitions for deadlock. So coming to the first very important definition of a deadlock is a continuous waiting state of a particular process is known as deadlock. This is the first definition of a deadlock. This is first definition of a deadlock. A continuous waiting state of a particular process is known as deadlock. What is the meaning of this? Already we have been known that. What is a process? A process can be thought of as it is a program under execution. In order to execute such kind of a process, it requires resources like CPU cycles, memory cycles, IO devices, etc. But all these particular resources are under the control of operating system. So before executing any particular process, first of all, you have to make a requisition to the operating system. I want these particular resources. So you have to make a requisition to the operating system. I want these resources. Once the resource is granted, then you're allowed to continue the execution. So once your execution is complete, again you need to return back all these particular resources to operating system. Okay, now, so whatever the resources you are requested, at the time the resource is not available from the operating system, then what operating system will do? Then operating system will going to be put your process in wait state. Then operating system will going to be put your process in wait state. There may be a chance that this wait state is not going to be changed forever. Hence, it is going to be called as deadlock. Hence, there may be a chance that this wait state is not going to be changed forever. Hence, it is going to be called as deadlock. This is one standard definition for deadlock. So we'll see some of the other definitions in a little while. Now we'll see. Let us assume that the system is consisting of some set of resources. The resources are named as R1, R2, so on up to Rn. In order to execute, the resources may be either its CPU cycles, or it may be memory cycles, or it may be IO devices, on up to CPU registers, etc. Already that's why I have been told that process definition is clearly a process can be thought of as it is a program in execution. In order to execute such kind of a process, it required resources like CPU cycles, memory cycles, IO devices, CPU registers, etc. That is what is the resources. The resources means in order to execute your process, you require CPU time, you require CPU registers, you require memory space, you require IO devices. This all comes under the category of resources of a particular process. So the resources are not only only one or two or any. It have WIF instances. You may have 10 registers. Okay, there are 10 in registers are there. You have two printers are connected to your network. Then there are two instances of printers are there. There are two tape drives are there. There are three tape drives are there. You can have any number of instances of resources. Now, so how the system model has been implemented? Now, the system has been implemented. The system model has been implemented by using three system calls. The system model has been implemented by using three system calls: request, use, and release. So now I have been told that before executing any particular process, whatever the set of resources you are required, you have to make a requisition to the operating system. I want these resources by using request system call. By using by using request system call. Once the resource is sanctioned, then using use system call, you are allowed to continue your operation. Once your execution is complete, you need to release your resources to the operating system by using a system call known as release. By using a system call known as release. Okay, so these are the three system calls which is required to implement any kind of a system. Okay, that's enough. Request, use, and release. So before executing a process, whatever the set of resources you're required to continue your execution, that can be done by using request system calls. Once the resources are obtained, you're allowed to continue your execution by using use system call. Once your execution is complete, you need to release the resources by using release system call. That's it. This is how the system model is implemented. Now we see some another definitions. Deadlock definitions is that a deadlock with the same resource type, a deadlock with a different resource type may be happen. Now we'll see. In a multi-programming environment, more than one process is competing for the resource. If any process is holding some resources and waiting for the resources held by some another process, similarly that process is also holding some set of resources and waiting for the resource held by this process, then both processes are not allowed to continue the execution, and this particular situation is going to be called as deadlock. Hence, this particular situation is going to be called as deadlock. Now we'll see with an example. Okay, deadlock with same resource type. Deadlock with same resource type. Deadlock with same resource type. Suppose my computer is having two tape drives. My computer is having two tape drives. My computer is having how many tape drives? My computer is having two tape drives. So in order to execute process, there are two processes running. There are two processes running in my computer system. In order to execute these particular two processes, they require tape drives. Process P1 two tape drives and process P2 also require two tape drives. Suppose what happens is the time T0 corresponds time, process P1 has been taken one tape drive. In time T0, time T1, process P1 has been obtained another tape drive. So that implies process P0 is holding one tape drive and waiting for the tape drive held by P1. Similarly, process P1 is holding one tape drive and waiting for the tape drive held by process P0. Then these two processes are not allowed to continue the execution. Hence, this particular situation is going to be called as deadlock. Hence, this particular situation is going to be called as a deadlock with the same resource type. Let us take another example. Deadlock with some different resource type. My computer is equipped with two resources. One is tape drive, one is printer. There are two processes running, P1 and P2. In order to execute process P1, it requires tape drive and printer. Process P2 is also required tape drive and printer. In time T0, process P1 is make a lock on tape drive, and time T1, okay, process P2 make a lock on printer. Now process P1 hold a lock on tape drive and waiting for the printer that is already held by P2. Similarly, P2 is also holding printer and waiting for the lock held by P1 of tape drive. Then both processes are not allowed to continue the execution. Hence, this particular situation is called as a deadlock. And this particular situation is going to be called as deadlock. This kind of a deadlock is going to be called as deadlock with different resource type. Simply, one line answer for a deadlock is a continuous waiting state of a particular process is known as deadlock. Now, how do you demonstrate deadlock characterization? What is the characteristics of a deadlock? In a deadlock, the process never finish executing and system resources are tied up and preventing other jobs from never starting. Understood? So how do you tell them? What is the necessary condition for causing a deadlock? What are the necessary conditions for causing a deadlock? There are 4 necessary conditions for causing a deadlock. That is, one is mutual exclusion. Number 2, hold and wait. Number 3, no preemption. Number 4, circular wait. Now in order to enter into a deadlock state, any one of the condition is sufficient. In order to enter into deadlock state, any one of the condition is sufficient. Licky, any one of the condition is sufficient. But the beauty in this, once the deadlock is obtained, if you verify it, all 4 conditions are simultaneously hold. That is the beauty of this. Okay, the necessary conditions in the sense, in order to enter into a deadlock state, in order to enter into deadlock, any one of the condition is sufficient. After entering into the deadlock, if you observe it, all 4 conditions are simultaneously hold. All 4 conditions are simultaneously hold. Very good. So before going to that one, okay, first of all we'll see what is mutual exclusion. The word itself, it says that mutual exclusion, at a time it can be used by only one person at a time. At a time it can be used by only one person at a time. So now let us, in order to understand this mutual exclusion point, now we'll demonstrate with an example. Okay, now mutual exclusion. So your computer is a collection of resources. The resources may be classified into 2 categories. Number 1 is shareable. Number 2, non-shareable resources. Number 1 is shareable. Number 2 is non-shareable. Shareable resource in the sense that resources can be accessed by any number of people at the same time. So no person is kept waiting for a shareable resource. No person is kept waiting for shareable resource. Best example, read-only file. The best example is read-only file. The best example is a read-only file. A read-only file, and that implies the file can be read by any number of users at the same time. Now, non-shareable resource, that implies that resource cannot be shared by more than one person at a time. That resource can be accessed by only one person at a time. That resource can be accessed by only one person at a time. Now, let us take an example. If one person is already using that non-shareable resource, if any other person is trying to access that particular resource, he has to be kept waiting. Now, let us take an example, printer. If printer is a non-shareable resource, in this mutual exclusion point of view, okay, it is printer is already taking one job and executing. Some another person is trying to execute at the same time. Sorry, if this particular job is not sanctioned, you have to wait until the printer becomes idle. Okay, that is printer is one of the CPU. CPU is already executing one process. At the same time, you require a CPU. Sorry, CPU is a non-shareable resource. CPU can be accessed by only one person at a time. Okay, so that implies that in case a non-shareable resource is already accessed by one particular process, then other processes are going to be kept waiting until this process has been completed its job. There may be a chance that that resource may not be released by this particular process, then all the rest of the processes are going to enter into deadlock stage. That implies the deadlock situation occurs only because of non-shareable resource. Non-shareable in the sense the resource is going to be shared by only one person at a time. At the same time, if any other person is trying to use that resource, The day the person is kept waiting, there may be a chance that the wait state is not going to be changed forever, and this particular situation is going to be called as deadlock. That implies at least one resource in a computer system, at least one resource must be held in non-shareable mode. That is, only one process at a time can use the resource. If any other process requesting the same resource, that must be wait until this resource has been released. This is first one. So the mutual exclusion causes, condition causes because of only non-shareable resources. There is no problem with shareable resources. Number two, hold and wait. What is this hold and wait? Just now I have told that. Okay, in a multi-programming environment, more than one process is competing for resources. Hello? Hello? ఎవరమ్మా? నమస్తే అమ్మా. నేను ఇంట్లో మరి ఇక్కడ 12:30 వరకు ఆన్లైన్ క్లాస్ లో ఉన్నాను. ఇంటి దగ్గరే నేను మరి మార్నింగ్ 2 hours కాలేజ్ ఉంటాను, తర్వాత ఇక్కడికి వచ్చేస్తాను. కెన్ యూ కమ్ టు మై హోమ్? ఓకే, యూ కెన్ కమ్ ఆఫ్టర్ 12:30. ఓకే, 12:30 తర్వాత రండి. జయరామ్ రా, జయరామ్ గారు ఓవర్టెక్స్ ఉంది కదా, ఓవర్టెక్స్ దగ్గరికి నుంచి పైకి అలా వస్తే సాయిబాబా గుడి ఉంటుంది, ఆ సాయిబాబా గుడి ఎదురు కమ్ ఆఫ్టర్ 12:30. ఓకే, sorry, again I'm getting back. Hold and wait. In a multi-programming environment, more than one process is competing for resources. In case if any process is holding some set of resources and waiting for the resources held by some other process. Similarly, this process is also holding some set of resources and waiting for the resource held by this process. Then both processes are not allowed to continue the execution, and this particular situation is going to be called as deadlock. Hence, this particular situation is going to be called as deadlock. Hence, this particular situation is going to be called as deadlock. Number three, no preemption. No preemption. What is no preemption? Suppose if your algorithms is not, your operating system is not having a capability of forcibly stopping the execution of one particular process and giving the control of the CPU to some another process, again the system is going to enter into deadlock state. Let us take an example. Suppose in a multi-programming environment, more than one program is simultaneously reside in main memory. While executing one program, in case if any program required an IO operation, CPU simply switches from one particular job to another job. But what happens is that one process is written a program, the program is structured in an infinite loop. What happens? Now the process, CPU is structured by this particular process, and CPU control will not going to be leave from one particular process to another process. That implies all rest of the process are going to be waiting for the CPU. They are entering into deadlock state. So how do you overcome this? Already we told that the CPU protection is done through timer control. The CPU protection is done through timer control. The CPU protection is done through timer control. Okay, after the specified amount of time allocated for this particular process has been completed, the CPU forcibly stopping the execution of this particular process and giving the control of the CPU to some other one. In case if the CPU is not, your operating system is not having such kind of an ability for forcibly stopping the execution of one particular process and giving the control of the CPU to some other one, then your process will going to be enter into deadlock situation. That's why your operating should have preemption. But if you not preemption, that implies there may be a chance that you are entering into deadlock. And finally, the last one is circular way. Let us take an example. There are n processors running, P0, P1, P2, so on up to Pn minus 1. P0 is holding some set of resources and waiting for the resource held by P1, and P1 is holding some set of resources and waiting for the resource held by P2. and P2 so on up to like this. Pn minus 1 is holding some set of resources and waiting for P0. Then no process allowed to continue the execution. And this particular situation is going to be called as deadlock. Hence, this particular situation is going to be called as deadlock. Now, how do you explain? Okay, we are talking in terms of theory. How do you explain the deadlock characterization? In order to explain the deadlock characterization in a graphical manner, we'll go for a technique known as a resource allocation graph, RAG. A resource allocation graph is a technique which can be used to describe a deadlock situation. How can you describe a deadlock situation? Before going to the detailed discussion about the deadlock situations, now let us define what is a graph. A graph is simply defined as is an ordered pair or it is a set of vertices and edges. A graph is simply defined as it is an ordered pair of vertices and edges. It is an ordered pair of vertices and edges. In this particular situation, vertices are two types. It may be a processes or it may be a resources. It may be a processes or it may be a resources. The processes are designated with P1, P2, so on up to Pn, and resources are designated with R1, R2, so on up to Rm. Okay. Now, coming to the second very important, this is vertices. The vertices may be either processes or maybe resources. Okay, and coming to the second one, edges. There are two kinds of edges to construct a resource allocation graph. Number one is requesting edge, number two is assignment edge. The requesting edge is written like this, Pi to Rj. That implies process Pi is requesting a resource for the Rj in order to complete the task. Process Pi is requesting a resource Rj. Process Pi is requesting for a resource Rj. And second kind of an edge is that assignment edge. So Rj to P, the Rj to Pi, that implies in order to complete Rj resource is been already allocated to process Pi. These are the only two kind of edges. This is purely a directed graph. You know that what is a directed graph? A directed graph, or you may call it as diagram, where all the edges are directed. Where all the edges are directed, there are only two types of edges are there. Number one is requesting edge, that is process Pi is requesting for a resource Rj, and number two assignment edge, that is the resource Rj already assigned to process Pi. The resource Rj is already assigned to process Pi. That's it. Now we'll see an example. Now there are three processes are running. Observe this diagram, everyone. Okay, there are three processes are running in my computer system, P1, P2, P3. There are three processes are running in my computer system. That is P1, P2, P3. Okay, P1, P2, P3. And there are four types of resources are there in my computer system, R1, R2, R3, and R4. There is, this dot indicates there is only one instance of resource type R1 is available. There is two instances of R2 type resources are there in my computer system. There is only one instance of resource type R3 is there in my computer system. There are three instances of resource type R4 is available in my computer system. This is what is this dots indicates. You can call it as there are three tape drives, two printers, so on up to like this. Okay, now this is processes and these are resources. These are called it as vertices. These are called it as vertices, and these are edges. This edge is called it as a requesting edge. Process P1 is requesting for a resource R1. Now that R1 is already allocated to process P2. The R1 is already allocated to process P2. Process P2 make a requisition to. Now process P2 is requesting for a resource R3. This is requesting edge. But R3 is already allocated to process P3. This is an assignment edge. Now, one instance of R2 is allocated to P1. Another instance is allocated to P2. These are all assignment edges. These two are. Okay, oh, and what is the need of representing in a graph? Now, whether the graph is in deadlock or not, we'll see now. Now we'll see. Process P1 is requesting process P1 is holding R2 and requesting for a resource R1. Process P2 holding R1 and R2 and waiting for R3. So P1 is in waiting state, P2 is in waiting state. Process P3 is holding R3 and not waiting for anyone. That implies at any moment of time the process P3 is completed. According to system model, it releases the resource. That resource is given to P2. Then P2 is successfully completed. It releases these two resources and this resource is granted to P1. P1 is continued. There is no deadlock situation in this. This is how you need to observe it. Or otherwise, simply, is there any cycle in this graph? No. Now, any cycle is formed in this graph? There is no cycles in this graph. 1, 2, 3, but it is in opposite direction. There is no cycle has been formed. 1, 2, 3, 4, 5, but there is no edges there. There is no cycle is formed, and the system is in safe state. That implies the system is not in a deadlock situation. The system is not in a deadlock situation. Is it clear? That is the advantage of constructing this particular graph. Okay. Okay, no need to observe each and every process, whether holding some resource, waiting for another one, holding some resource, waiting for another one. Simply, you can check it whether the graph is having a cycle. In case if the graph is having a cycle, you may have a deadlock. Why I used a may. We will see at a later stage in the next example. This is how do you represent a deadlock situation using resource allocation graph. Now we'll see by means of an example. Okay, the cycle does not leads in deadlock state. Cycle does not guarantee the system is in deadlock state. Cycle does not guarantee that the system is in deadlock state. Cycle does not leads to deadlock state. What is the meaning of it? Let us now you see. I'll tell you in both the ways. In this, there are three. In this example, there are three processes running: P1, P2, P3. In a similar manner, these are vertices. There are another 4 vertices of resources: R1, R2, R3, R4. There is one instance of R1. There is 2 instances of R2, 1 instance of R3, and 3 instances of R4. Process P1 is holding R2, requesting for a resource R1. Process P2 holding R1, R2 and waiting for R3. Process P3 holding R3 and waiting for R2. Now you see that process P1 is in waiting state. Why? Because it is holding R2 waiting for R1. Process P2 is also holding R1, R2 and waiting for R2, R3. Process P2 holding R1, R2 and waiting for R3. Process P3 is also holding for R3, waiting for R2. All P1, P2, P3 all are in waiting state. That is, all processes are in deadlock. All processes are in deadlock state. Now simply you can say that now you see, observe it. 1, 2, 3, 4, 5, 6. Cycle is formed. Then that implies now the process is in, now the system is in deadlock state. Once you have got a cycle in the graph, that indicates that now the system is in deadlock state. Once you have been got a cycle in this, now the system is in deadlock state. That implies cycle does not leads to deadlock. If a computer system is entered in a deadlock state, that implies there is a cycle in the system. But cycle does not lead to deadlock. Let us see the example. Now in this, there are P1, P2, P3, P4, 4 processes are running. These are vertices and another 2 vertices, R1, R2. There are 2 instances of R1 is available. There are 2 instances of R2 is available. Now, what happens? Now in this particular one, now we observe it. You have got a cycle. Hence you can say that it is in deadlock. But this particular one is not in a deadlock state. Can you see this? Now process P1 is holding R2 waiting for R1. This is in waiting state. Process P2, P3 holding R1 waiting for R2. Yes, this is in waiting state. P2 holding R1 not waiting for anyone. P4 is holding R2 not waiting for anyone. Hence, according to system model, after execution of this one, the resource 1 is released and resource 2 is also released. This resource is going to be sanctioned to P1. This resource is sanctioned to, and this R2 resource sanctioned to P3. Both P1 P3 are continue. There is no deadlock in this particular situation. No one is continuously waiting. That implies cycle does not guarantees that the system is in deadlock. But if a deadlock is occurred, there is a cycle in the system. But a cycle does not, may not is a deadlock. Now how can you explain this? Why this is happened in the sense there is multiple instance of resources are there. There are multiple instances of resources there. Suppose if your computer is having a single instance of each resource type, then cycle leads to deadlock. Deadlock implies cycle. So both are satisfied. So that is cycle leads to deadlock and deadlock leads to cycle. But in case if a computer system is having multiple instances of each resource type, cycle may not lead to a deadlock, may not lead to a deadlock, but deadlock leads to a cycle. Thus, is it clear? That is, if a graph contains no cycles, no deadlock. If a graph contains a cycle, if only one instance of resource type, then it is in deadlock. If several instances for each resource type, possibly may not have a deadlock. That's it. This is how do you explain the deadlock characterization using resource allocation graph. Okay, how do you explain deadlock situation using resource allocation graph? Now we can clearly understood that what is a deadlock. Now how to handle this particular deadlock situation? In order to handle this particular deadlock situation, we have three kinds of methods. We have in order to handle deadlock situation, we have three methods. Number one, we can use a protocol to ensure that the system will never enter into a deadlock state. What is this? We can use a protocol. You know what is a protocol? A protocol is a set of rules and conventions to share the resources. So we have to write a protocol in such a way that the system will never enter into the deadlock situation. Point number two, allow the system to enter into the deadlock. Allow the system to enter into the deadlock, then use, recover, then recover. Allow the system to enter into the deadlock, observe it. Once the deadlock is obtained, use some recovery algorithm to break the deadlock and continue the execution. This is second type. And the third kind of solution is that ignore the problem together and presented the deadlocks will never occur in a system used by this is ignore the problem and pretend that deadlocks will never occur in the system. This is the solution most of the operating system will use. If deadlock is encountered, the user is going to be forcibly stopping the execution of any one of the process by end of the processes. Okay, most of the operating system, including Unix, is also use this particular technique. Now, coming to the first one, ensure that the system will never enter into the deadlock state. That is, it can be done by using two techniques, deadlock prevention and avoidance. We'll see what is this particular deadlock prevention and avoidance. Okay, so what is deadlock prevention and avoidance? We'll see it meanwhile. Number two, allow the system to enter into a deadlock state. You have to write one algorithm to observe whether the system is in deadlock state. And once you have been observed that the system is in deadlock state, then you can recover by using another algorithm. Now, coming to the next one. We'll see one of the solutions of this. Coming to the first one. So, deadlock prevention. That is, the first solution for handling deadlocks is that we can use a protocol to ensure that the system will never enter into the deadlock situation. In order to meet such kind of a requirement, we have two things. Number one, deadlock prevention. Number two, deadlock avoidance. There are two techniques are there. Number one is deadlock prevention. Number two, deadlock avoidance. What is deadlock prevention and what is deadlock avoidance? Deadlock prevention in the sense, what are the necessary conditions which causes for a deadlock. What are the necessary conditions which is causing for a deadlock? You please try to see that the conditions will never occur in the system. Understand my point? What are the necessary conditions which are causing for a deadlock? You please try to see that conditions will never occur in the computer system. That is what is deadlock prevention. Deadlock avoidance. Next one, deadlock avoidance. You have to allocate the resources in such a way that the system will never enter into the deadlock state. So the resources is completely under the control of operating system. So that your operating system must see that there is always one process has to be continued execution. That implies the resources must be allocated in such a way that the system will never enter into the deadlock situation. Now coming to the deadlock prevention. What I told in deadlock prevention, what are the necessary conditions which is causing for a deadlock? You please try to see that conditions will never occur in the system. So what are the necessary conditions which are causing for a deadlock? It is 4 conditions: mutual exclusion, hold and wait, no preemption, circular wait. These are the 4 conditions what you are going to be getting. Coming to the first one, mutual exclusion. So already I told that your computer system is equipped with 2 kinds of resources, shareable and non-shareable resources. We are not getting any deadlock situation with shareable resources. We are getting a deadlock situation with only non-shareable resources. Okay, so that implies non-shareable resources. Now, what he has been told that what are the necessary conditions which is causing for a deadlock? You please try to see that the necessary conditions will never occur in a system. How can you do this? Please, simply one scientist has been given a solution that please remove okay. So printer is a non-shareable resource. Already I told that printer is a non-shareable resource. Okay, printer can be shared by only one person at a time. If already one person is taking the printer on the printer, if another person is waiting for the resource, printer definitely has to be kept waiting. That's it. There may be a chances that this waiting state is not going to be changed forever. Hence, it may be enter into a deadlock state. That implies the deadlock situation is occur because of non-shareable resource. Then the solution for this one is one scientist told that remove all non-shareable resources. Printer, it is a non-shareable resource, you can remove it, there is no problem for the computer. Suppose CPU is also a non-shareable resource. CPU can be used by only one process at a time. So if you want to remove the CPU, if you remove a CPU, then what is the need of doing all this? So it cannot be possible. So you observe it. I am telling one of the solution, and I'm telling that the solution is not possible. Finally, my conclusion is that we cannot see that deadlock prevention will going to be happen. Okay. So now the solution is remove non-shareable resource. If you remove non-shareable resource, the computer system will not going to work at all. That's it. That's why it is not possible. Coming to the second one, hold and wait. What is hold and wait? Already I told that in case if any process holding some set of resources and waiting for the resources held by some another process. Similarly, that process is also holding some set of resources and waiting for the resource held by this process. Then both processes are not allowed to continue the execution. Hence, this particular situation is going to be called it as deadlock. Hence, this particular situation is going to be called it as deadlock. The solution, what we have been seen is that we'll see what solution. Must guarantee that whatever a process requests a resource, it does not hold by anyone. So you please try to see that whatever the resource you are requesting, the resource should not be locked by any other process. How can you guarantee that? Okay, that's why one scientist has been told that, okay, solution is that before requesting for any particular resource, first of all, you should have a none. You should release all the resources, whatever you have been already acquired. You should release all the resources, whatever you have been already acquired. But what happens? This is also what happens is that resource utilization becomes very low and starvation is going to be possible. Let us take an example. There are 2 processors running, P1 and P2. In my computer system, there is 2 resources, tape drive and printer. In order to execute process P1, it requires tape drive and printer. In order to execute process P2, it is also required tape drive and printer. We have passed a process P1 holding tape drive, waiting for printer. Process P2 holding printer and waiting for tape drive. Then process P1 is making a requesting for printer. Immediately operating system says that release your tape drive. Then tape drive is released. Similarly, for process P2, printer is released. Then printer is sanctioned to P1 and tape drive is sanctioned to P2. Again, process P1 is holding printer, waiting for tape drive. Process P2 holding tape drive, waiting for printer. Then both are ending. So the both are going to be in deadlock situation. That becomes, what happens is that, again, it cannot be possible. Okay, only resource exchange is done, the execution is not done. Another scientist has been given another solution, that is starvation. Another scientist has been told that what are the set of resources has been required to execute a particular process. Please try to all resources before starts its execution. He is given this solution. But what is this particular solution? Suppose in order to execute process P1, it requires tape drive and printer. But while using tape drive, it does not require printer. Okay, let us take it is a 20 minutes of job. First 10 minutes, the process P1 is spending with tape drive, and last 10 minutes spending with printer. If two resources are allocated at the same time, what happens is that while doing operation with the tape drive, the printer is going to be sitting idle. While doing operation with the printer, the tape drive is sitting idle. That becomes resource utilization becomes very low. Suppose if you are allocating all the resources before starting the execution of a particular process, resource utilization becomes low. The main goal of an operating system is that to keep all the resources busy at all the times. That's why it is failed. In case if you are having the second solution in case before requesting any particular new resources, first of all you should have none. If you implement that particular resource, the only resource exchange is done, but deadlock starvation is possible. That's why this condition is also not practically implemented. Now, third one, no preemption. No preemption. What is no preemption? No preemption in the sense, if your operating system is not having a capability of forcibly stopping the execution of one particular process and giving the control of the CPU to some another process, again the system is in deadlock state. Suppose if you are given a permission, yes, you are allowed to forcibly stopping the execution of one particular process, then what happens is that one program is always runs in the system kernel, which is known as operating system. So that process is completely running. What you are doing is that your operating system is forcibly stopping the program itself. What happens? Your entire system is going to be down. That is the problem. So this is also not practically possible. If a process that is holding some resource requesting for another resource cannot immediately allocate it, all resources currently be released. Preempted resources are added to the list of resources which is the process waiting. The process will be restarted only when it has regained its old resources as well as new resources is requesting. That's it. So this is also not going to be possible. Now, coming to the last one, circular wait. Coming to the last one. Coming to the last one, circular wait. What is this particular circular wait? P0 is holding some resources, waiting for P1. P1 is holding some set of resources, waiting for P2. So on up to Pn-1 holding some resources and waiting for the resources held by P0. Then simply the solution is that abort any one of the process. Then once aborted, whatever the resources which has been holded, it has been given to next process so that the deadlock situation is going to be overcome. But the situation is that whatever the process you are aborted, in case if it is an operating system, what happens? The entire system is going to be down. That's why the circular wait is also not possible. That is, impose a total ordering of all resource types and require that each process require resources in an increasing order of enumeration. That is circular wait. So, this is not possible, this is not possible, this is not possible, this is not. We have been told some solutions, but the solutions are not practically possible. So, my conclusion is that deadlock prevention, that is, okay, what are the necessary conditions which is causing for a deadlock? We cannot ensure that the system, we cannot ensure that will never occur in a system. So, this definitely occur. So, there is deadlock is compulsory. Now, so what is deadlock prevention? What are the necessary conditions which is causing for a deadlock? You please try to see that that never will occur in a system. That never occur in a system. So that that never will occur in a system. Then it is not possible. That's why we enter into next one, deadlock avoidance. What is deadlock avoidance? So what is deadlock avoidance? You need to allocate the resources of a particular process. You need to allocate the resources to a particular processes in such a way that the system will never enter into the deadlock situation. Whatever the resource allocation ordering is done in such a way that the system will never enter into the deadlock situation. The system will never enter into the deadlock situation. That is what I told. And in order to do this kind of a thing, in order to do such kind of a thing, so the operating system has been given an additional prior information, what kind of resources are available, what kind of resources are required for each and every process at what moment of time. Otherwise, it is not possible. So, it requires that the system has some additional prior information available. What that additional prior information should be required? So, what is the maximum number of resources which is required to complete a particular process? What is currently it is required? The rest of resources may be required at what moment of time? You need to allocate this. That implies, in order to practically implement deadlock avoidance technique, in order to practically implement a deadlock avoidance technique, the operating system should have an additional prior information relating to a particular process in such a way that what are the maximum number of resources that is required to each and every process, and what are the set of resources which is required at what moment of time. It should be known to your operating system, so that the operating system will going to be allocate the resources in such a way that the system will never occur in a deadlock situation. That is the first one. The simplest and most useful model that requires that each process declare what is the maximum number of resources of each type that may need it. In order to complete your process, what is the maximum number of resources of each type you needed? First, you clearly mention it. Number two, the deadlock avoidance algorithm dynamically examines. Dynamically, that is, at the time of execution, resource allocation state to ensure that the system will never enter into a deadlock situation, that is circular wait. That implies whatever the currently available, this is, you please observe it, circular wait condition. That implies whatever the currently available resources must be, you need to define a sequence in such a way that the currently available resources must be satisfy any one of the waiting process. The currently available resources must be satisfy any one of the waiting process. So the CPU has to be scheduled the jobs in such a way that, okay, the CPU has to be define a safe sequence, the CPU has to be define an order of sequence, order of execution of processes in such a way that the currently available resources must be satisfy any one of the waiting process. Okay, now point number 3. The resource allocation state is defined by the number of available resources and allocated resources and the maximum demands of the processes. The resource allocation state is defined in terms of what is the maximum number of resources which is required by each and every process, what is already currently held by each and every process, and how many need they are required, that is maximum minus allocation. That's why the ordering is called as in what order the resources must be allocated in such a way that the system will never enter into the deadlock state. The system will never enter into the deadlock state. The only one condition is that, very important condition is that whatever the currently available resources are there, it should satisfy any one of the waiting process. You need to define an ordering like this. That ordering is going to be called it as safe state. You may call it as safe state sequence. The safe state sequence must be defined in such a way that the currently available resources must be satisfy any one of the waiting process. That's it. Now, in order to do this, in order to define this particular save sequence, in order to define this particular save sequence, what the operating system is going to do? Whenever a process is requesting for a particular resource, immediately operating system observes that whether I am eligible for immediately sanction that resource or no. By sanctioning, you try to see that the system will never occur into the deadlock state. Why? Because after sanctioning, the process executed, whatever the set of resources has been released, again it should be satisfy any one of the waiting process. This is recurrently satisfied, all jobs are completed from the ready queue. So that's why when a process requests an available resource, system decide that if immediately allocation will leave the system in safe state or not. After immediately allocating it, in case system is in unsafe state, that implies whatever the currently available resource which not satisfying any one of the waiting process, then the system is going to be enters into a deadlock state. Then immediately the request cannot be granted. That's why you need to decide. You need to decide whenever a process is requesting for a particular resource, whether immediately allocated or not. In case, if you immediately allocate it, the system is immediately safe state. Okay, you should be see that it is in safe state. If it is not in safe state, please don't try to allocate it. Okay, now what do I mean by safe state? The system is in safe state if there exists a sequence P1, P2, so on up to Pn in such a way that after executing P1, whatever the set of resources which is available, it should satisfy P2. After executing process P2, whatever the set of resources which is available, it should satisfy process P3. So on up to like this. That implies the currently available resources should be satisfied to the next process, like this. That is, the system is in safe if there exists a sequence P1 to Pn of all processes in the system in such a way that Pi, each Pi, then the resource Pi still request can satisfy the currently available resources plus resources allocated by Pj, j is less than I. That's otherwise the resources are not going to be sanctioned. That is, if Pi resource needs are not immediately available, then PIs can be wait until all Pj has been completed. Yes, whatever the resources you are requested, if the resources are not available from the operating system, immediately you need to wait until all other processes has to be completed and there must be released the resource and it is going to be sanctioned to you. Alright, sorry. When a Pj is finished, Pi can obtain needed resources and execute and return all the resources and terminate the process. You know what is this? Why? Because system model has been implemented by using three system calls: request, use, and release. Okay, so once the process execution has been successfully completed, you have to return back all the resources to your operating system. Now, if process Pi terminates, I plus 1 can obtain, it needs resources and so on like this. That implies after completion of Pi plus 2 can be continued by releasing the resources of Pi plus 1. That implies currently available resources must satisfy any one of the waiting processes. Otherwise, it is not possible. There is a safe sequence. So, in case if you orderly execute in safe sequence manner, the system will never enter into the redom. It is the responsibility of the operating system to define a safe sequence in such a way that the system will never enter into the deadlock state. So, finally, I conclude with this topic. If a system is in safe state, that implies there is no deadlock. If a system is an unsafe state, there may be a possibility for getting a deadlock. So, you have to write an algorithm in such a way that the system will never enter into an unsafe state. So the resources must be allocated in such a way that the system must be always define a safe sequence. That is. So this can be demonstrated by means of a small example. This can be demonstrated by means of a small example. What is this example? Now we are going to see. Okay, by means of a problem. This problem is already given in exam. Okay, so how examination in GATE examination the question has been given. I'll tell you. Now there are three processes running in my computer system. ఎవరమ్మా J2 నుంచి అయితే M1 example. There are three processes running in my computer system, process P0, P1, P2. There are total number of resources available in my computer system is 12 tape drives. In order to complete process P0, it requires 10 tape drives. In order to complete process P1, it requires 4 tape drives. In order to complete process P2, it requires 9 tape drives. But the current needs of each and every process, process P0 holds 5 tape drives, process P1 holds 2 tape drives, process P2 holds another 2 tape drives. So the total number of resources consumed is 9. So the total available resource is 9. Available is 12. 12 minus 9, there is only 3 resources are remaining. Now, thus process P0 is holding 5 tape drives and requires another 5 tape drives, that is a need. This is going to be called as remaining.
చందక భవ్య హరి చందన కావాల భవ్య హరి చందన చందక
చందక భవ్య హరి చందన
అయితే అలాగే అంటే స్కూల్కి వెళ్ళాలంట సర్టిఫికేట్
నుంచి పర్లేదు
చందక రాష్ట్రం
సర్నేమ్ లాస్ట్ వచ్చింది, లాస్ట్ రావాలి. So in order to complete process P0, it requires 5 additional resources. In order to complete process P1, it requires another 2 additional resources. Process P2 requires another 7 additional resources. Now you see that the requirement of this process P0 is 5, 2 and 7. The currently available is 3. Currently available is 3. Now currently available 3.
ఓకే మన ఇద్దరికి ఇనిషియల్స్ THN నుంచి ఎలా చందుతాను రాయాలి
CHN నుంచి
మా మేడం THN చాలా TH
yeah Anu. Please remember. Okay, now the currently available resources is only 3. So the 3 is satisfying process P1. Okay, so that now the available 3 resources is given to process P1. So that already P1 is holds 2 resources. Now it is allocated with 3, 3 plus 2. Now the total 5 resources are available now. Now among this P0 and P7, 5 is satisfied by P0. So that the next process is P0. So all 5 resources is given to them. Already it holds 5. 5 plus 5 total available is now 10. Now the 10 is satisfying process P2, so that you can give to process P2. So the resources must be allocated in the sequence P1, P0 and P2. In this order, the system is in safe state. The currently available resource must be satisfied any one of the waiting process. This is good. Now, suppose let us take they have an examination. They have been given a situation. They have been given a situation that if process P2 is requesting one resource, it is immediately sanctioned it without saying in it. Then what is currently available resources now? Is only 2. So 5, 2 and remaining is 6. 5, 2, 6, which one is satisfying? So 2 is satisfying. So that this 2 is given to process P1. So 2 plus 2, the currently available resource is only 4. Now this P0 requires 5 and P2 requires 6 resources. So the 4 is not satisfying any one of the requests. any P0 and P2, hence the system is in deadlock state. That's it. So that's why what I'm telling is that whenever a process requesting for a resource, you please don't try to sanction immediately. By sanctioning whether the system can be defined a safe sequence or not. In case if it is unable to define a safe sequence, please don't try to sanction that. That is going to be called as. In examination, the question is, okay, the P2 is requesting for additional resource. One, it is immediately sanctioned. Now, whether the system is in safe state or unsafe state. The system is in unsafe state, the system is in deadlock. That's it. This is what is an example. It's clear. Now, before go for the next very important discussion is Banker's algorithm. So this is not completed in short span of time, but will going to be covered tomorrow. And so today what we have been seen is that what is a deadlock? What is the necessary conditions for a deadlock? What are the different methods for handling a deadlock? And this one of the method is that deadlock prevention. In deadlock prevention, what are the necessary conditions which is causing for a deadlock? You please try to see that the conditions never occur in system, which is not possible. And after that, we have been seen a safe state. We need to define a safe sequence in such a way that the system will never enter into the deadlock state. That implies whatever the set of resources which is currently available, it should satisfy any one of the waiting process. It should satisfy any one of the current waiting process. This is what we have been seeing. Now, this solution is now applied to multiple processes with multiple instances. Okay, how can we apply? We'll see in the next session. That is in Banker's algorithm. We'll see that kind of a discussion tomorrow. That is Monday. Is it clear, everyone? Okay, that is stopping my presentation for today. And thank you, everyone. Is anybody there? Today's my presentation is over. Yeah, the presentation is completed. Again, Monday. Okay. I hope tomorrow is Monday. Yes. Okay. Okay. Monday same time. Okay. Thank you. Is everything right? Can I stop?